So welcome everybody to this second seminar of the official IAU G2 online conference series. This time we have May Pedersen, who is now late in the evening in Sydney. So thank you very much, May, for inviting or for accepting our invitation to give this interesting seminar. And I'm going to say a few words about your career, just for people to know you better. Even I'm sure that many people know you already. So May started her astrophysical studies in Aarhus University in Denmark, together with Vicky Antoki and Fran Brunhal, working on flares in 8 stars. And then she went to one of the important spots dealing with asteroseismology of massive star in Leuven to do the PhD together with Connie Ertz and Peter Papix. And she defended the thesis in 2020. So it was in the middle of the pandemic, and it was great that we were able to see your defense online. This was very, very nice. And after that, she went first to Kavli Institute in California for a couple of years. And a few months ago, she moved to Sydney to spend some time there. And basically, her interests are mostly asteroseismology of massive stars. I don't know if you also go to intermediate mass stars and low mass stars, you will tell us. And she's now one of the experts on the analysis of data provided by Kepler and also TESS. So again, thank you very much for telling us about your studies. And whenever you want, you are welcome.
All right. Minimize you all. Okay. Hi, everyone. So first of all, I'd like to thank you for the opportunity to come and give this seminar. As you might have guessed already from reading my title of my talk and perhaps even the abstract, the talk today is going to focus on asteroseismology, and more specifically, asteroseismology of B-type stars and what the pulsations in these types of stars can tell us about the interior mixing and angular momentum transport for these stars. So as a starting point, let's start by having a look at what the interior structure of these stars look like. So on the left on this slide, you see a 3D model of a B-type star where we have a slice in the middle down to see what the interior looks like. So for the interior structure, we generally divide the inside of the star into 3 different regions. So we have the convective core. Outside of that, we have the radiative envelope. So we have energy transport by radiation. And in between the two, we have a transition region as well. So during the main sequence evolution of these stars, the core hydrogen burning is happening dominantly through the C and O cycle, where we have isotopes of carbon, nitrogen, and oxygen that act as catalysts during the nuclear burning. Now, out of all these reactions, the one that takes the slowest is where we are converting nitrogen into oxygen. And because this reaction is slow, that means that over time, we end up building up an excess amount of nitrogen in the cores of the stars. And if we then have mixing happening in the envelopes of the stars, that means we can bring excess nitrogen from the core to the surface and have the surface abundances modified in that way. Additionally, we can also bring new hydrogen fuel from the envelope into the convective core. And so what's important here is that the convection itself, since it happens on such short time scale and a very dynamic, that means the mixing that is taking place inside the cores of these stars is very efficient. So any hydrogen we have inside the convective core, we can use as fuel during the nuclear burning. And any additional hydrogen that's going to enter the core, we can also use as fuel. So having mixing inside the star is going to extend the main sequence lifetime compared to in standard models without mixing. And also it's going to increase the helium core mass obtained at the end of the main sequence evolution. Now the mixing inside the stars we can represent using these types of mixing diagrams, as I call it, where we have the efficiency of the mixing on the y-axis and the mass coordinate on the x-axis going from the center towards the surface. Now these types of mixing diagram I split into 3 different groups, 3 different regions. That corresponds again also to the 3 different regions in the interiors of the star. So we have the convective core in gray. We have additional mixing from the convective core at the convective core boundary. And on top of that, we have mixing in the envelopes of the stars. So the problem we have when we try to study stellar evolution is that these mixing profiles are not necessarily that well constrained, at least from in-situ observations. And so one of the goals, one of the things I've been working on is using asteroseismology to try to study these interior mixing properties of the stars. So asteroseismology is the study and interpretation of stellar pulsations. The frequencies of these pulsations change depending on stellar parameters such as mass, radii, and ages. And also since the oscillations penetrate deep into the stellar interiors, they also get modified as the structure of the stars change. And in that way, by studying these pulsations, we can learn something about their interiors. So asteroseismology has 2 main goals. One is to exactly derive these fundamental stellar parameters. And the second goal is to try to provide constraints on the interior properties of the stars, such as the internal mixing, angular momentum transport, and magnetic fields. And maybe not surprisingly, the focus on my talk is going to be on this second point here. Now, if you want to study stellar pulsations, the good news is that there are pulsating stars all across the HR diagram, as shown in this type of asteroseismic HR diagram, where each one of these shaded regions corresponds to a place where we find a different type of pulsating star. Now, I really like this HR diagram, and that's because it tells me if at any point during the evolution of the star, it passes through any of these shaded regions, then it should start to pulsate. And if it's pulsating, that means we can learn something about the interior properties of the stars. Now, the pulsations themselves we see as a variation in the surface brightness of the star. And when we want to do asteroseismic modeling and studying stellar interiors, astroseismologists really want to make sure we observe the stars for a long time and have long light curves, as we call it. And why is that? So I'm trying to illustrate that with the figures here, where on the top we have a light curve of a gravity mode pulsator observed by Kepler. And on the bottom 3 panels, you see the Fourier transform of that light curve, assuming 3 different lengths of the time series. So in the left-hand panel, we assume that the light curve is 30 days in length. In the middle one, it's 90 days, and the final one is 180 days. And so what you see, as we're increasing the length of the time series, the resolution, frequency resolution increases, and we start being able to detect frequencies we might not have been able to do before. And also because of this narrowing of the peaks, means that we can measure the frequencies to a much higher precision the longer we observe the stars for. And the better precision we get on the frequencies, the better constraints we can get on the interior properties of these stars. Now, the type of data, the best type of data we have available at the moment to do asteroseismic studies comes from the Kepler space mission, the nominal mission, which observed the same patch of the sky for 4 continuous years. So that means at least every 30 minutes, we have a measurement of the brightness of the star for 4 years in total. Now, the choice of the field of view of Kepler is such that the highest mass pulsating star that was observed by the nominal mission is the slowly pulsating B-type stars, which you find right here in the middle of the asteroseismic HR diagram. So the slowly pulsating B-type stars, they oscillate in gravity modes, where gravity acts as the dominant restoring force behind the oscillations. And they're called slowly pulsating because the period of the oscillations are between half a day to 5 days in total. Now, one unique properties of these gravity mode pulsators, these slowly pulsating B-type stars, is their oscillations form what we call period spacing patterns, which when we model, we can get additional constraints on the interior properties of the stars. So before I get to the patterns themselves, I want you to get a bit an idea of how asteroseismologists classify pulsations. And we do so according to 3 different quantum numbers, which are associated by the number of nodes that an oscillation has. And since the oscillations occur in 3 dimensions, that means we have 3 different types of nodes. So here, in this plot, what I'm showing you here on the left is in white the nodal lines of the oscillations, whereas red regions are regions of the star that are moving inwards, and blue regions are regions of the stars that are moving outwards. So there are 2 types of surface nodes. One is the degree L, which gives you the number of nodes, total number of nodes on the surface of the star. The azimuthal order M is the number of nodes that crosses the equator. And finally, the third type of nodes we have is the interior radial orders, the interior radial nodes, which are concentric nodal shells that we have. And so here on the bottom, you see different configurations of what the pulsations looks like, depending on the mode identification of the oscillations. Now, the reason why I wanted to introduce this is to help understand a bit how the period spacing patterns look like and how they're constructed. So the period spacing patterns utilizes the property of gravity modes, that they're roughly equally spaced in period. So what I mean by that is that if we have oscillations that have the same L and M value, but are different, with the only difference being the number of interior radial nodes, then the period differences between these oscillations is roughly the same, as you can kind of derive from these equations above, where on the equation on the left gives you the period of the oscillation. And on the right, we have the asymptotic period spacing, which is essentially a function of the integral of the Brun-Weishaler frequency, the inverse of that. So in the case of a non-rotating, chemically homogeneous star, if we go and calculate the period differences between our oscillation P2 and P1, then that difference is going to be roughly the same as between our oscillation P3 and P2, and so forth. So if we take these period differences and plot them as a function of period, that gives us the period spacing pattern. And what we tend to do in addition to this is connect these dots, these data points, with a line that helps us see if we have any deviations from the period spacings themselves. Now, this is the case if we have a non-rotating chemically homogeneous star. So naturally, these period spacing patterns are going to change as soon as we introduce rotation and stellar evolution. Yeah. So for as soon as we have rotation happening for the star, what's going to happen is that the rotation introduces a slope to these period spacing patterns that's going to depend on how fast the stars are rotating. Yeah. So the idea here is generally that modes that travel in the direction of the rotation is going to take less time to move around the star when it's traveling in the direction of the rotation, contrary to modes moving in the opposite direction. And so in this case, we have modes that are kind of traveling in the same direction as the rotation, and this shortens the periods and also decreases the period spacing values as well. And fitting these slopes helps us derive the mode identification as well as the rotation rates of the stars. So in addition to this, now we talked about rotation. The next part is what about chemical gradients when the stars are not chemically homogeneous? In this case, we also see deviations from having these constant period spacing patterns that are caused by the introduction of chemical gradients inside the stars. So for a star evolving on the main sequence, we naturally develop these kind of chemical gradients as hydrogen is converted into helium in the cores of the stars. So here on the left, I'm showing you 3 different profiles of the star, where we have the hydrogen mass fraction profile as a function of interior mass coordinates for about the inner 35% of the star. Each one of these profiles corresponds to 3 different main sequence evolutionary stages, where blue, we're near the C8 main sequence. We have orange is near by the middle of the main sequence, and green is towards the end of the main sequence evolution. Correspondingly on the right, I'm showing you what the period spacing pattern looks like and how it changes at each one of these 3 different main sequence evolutionary stages. So what we're seeing is that as the star evolves, we start developing deviations from these very smooth patterns, and also the average level of the pattern itself starts to decrease as the stars become more evolved along the main sequence. Now, these kind of deviations are caused by the development of this chemical gradient, which the effect of is to trap the oscillations and then giving rise to these deviations from a uniform pattern. And so if we have mixing occurring inside the stars, that's going to change our gradient and therefore also impact what our period spacing patterns look like as well. Okay. So to summarize this and to make comparison also, if you look at observed period spacing patterns, I'm showing you here an example of 7 different period spacing patterns from SPB stars that were studied, observed by Kepler. In summary, the slope of these patterns depends on the interior rotation of the star. The average value depends on the mass and the age of the star, whereas the exact morphology depends on both the age and the mixing properties of the stars themselves. So by modeling these patterns, we can learn something about each one of these properties of the stars themselves. Now, prior to this research and studies I carried out on this type of asteroseismic modeling of SPB stars observed by Kepler, there were only few prior cases where such modeling had been done. And so that's what I'm trying to illustrate here, where you see on the left is another HR diagram, where the shaded region here now corresponds to the instability strip of the SPB stars, so where we expect to find these types of pulsators. The more yellow region corresponds to the higher number of excited pulsations we expect to see compared to the darker blue regions. So initially, prior to the studies and research I did, there were about 4 such stars that had been modeled using Kepler data. And what we ended up doing was increasing the sample to 26 SPB stars that we modeled simultaneously. The kind of data we had available comes in different formats, let's say. So we have the period spacing patterns, which we got from the light curves of the stars themselves. On top of that, we have from spectroscopy, we have the effective temperatures, the surface gravities and metallicities of the stars. And with the Gaia distances, we also have a luminosity available. Now, each one of these observables we've used in different ways. So the period spacing patterns are the values that we're actually comparing to the models, whereas the other parameters we're using to limit the range in models that we are considering for the asteroseismic modeling themselves. So they're not part of our merit function to determine the best matching model, but it's used to limit the range of relevant models for the modeling itself. Now, the models themselves that we're studying, the stellar models, we can express as being a function of a set of fixed input physics, psi, and a set of varied parameters, delta. So in the case, so to give an example, the fixed input physics would correspond to the shape of the interior mixing profile that we choose, whereas the varied parameters would be the mass, metallicity, age, and the mixing parameters that were adopted. So the stellar models themselves we computed using the Stellar Structure and Evolution Code MESA, which were then had derived their oscillation properties using the pulsation code gyre. And from gyre, we add an additional free parameter, being the rotation frequency of the star. Now, the modeling itself, we try to reduce the number of MESA models and gyre models to compute, to try to make the kind of asteroseismic modeling having this high number of SPB stars to study feasible. And so the way this was done was essentially we have one grid per fixed, let's say, interior mixing profile, where we have a whole grid of models. Based on this grid, we calculate a statistical model that we use to predict what the oscillations would be at different points that were not included in the original grid. So the way this works for the asteroseismic modeling then in the end is we look at the position of the star in the HR diagram, zoom in on this region. So originally, if we only use the grid itself for the modeling, we would have about 612 stellar models with 5 different rotation rates for the oscillation calculations. Using the statistical models, we can easily increase the number of models inside that range to 100,000, which is what we used for each star. And from this, we compared the observations to the observed period spacing values to the theoretical ones using the Mahalanobis distance as a mirrored function. So to give a few examples of what the observed versus theoretical period spacing patterns looks like, you see the result here, where the full curves corresponds to the observed period spacing patterns, so the solid lines. The corresponding best fit is seen in a fainter colored line, so not a solid line, let's say, here in the background. So as you can see, we obtain quite a good fit to the observed period spacing patterns. So that's good. But what we really want to get at is what the interior mixing and rotation properties of these stars are. So as the first step, I'll copy the internal mixing and say for this step of the analysis, we considered a total of 8 different interior mixing profiles, which consists of 2 different choices of the convective boundary mixing. So the top rows of panels shows you the case where we assume the mixing is decreasing exponentially as we move further away from the core. The second row corresponds to the case of convective penetration, where we're assuming that the mixing stays constant throughout this extra convective boundary mixing region. On top of that, we consider 4 different shapes of the envelope mixing, which when combined with the 2 different shapes of convective boundary mixing gives us a total of 8 different profiles. So for each one of these profiles, we calculated stellar structure and illusion models, a grid of those, and then try to see which ones of those did the best at reproducing the observed period spacing patterns. So this is essentially the result. So this is a repetition of the mixing profiles from before, where now the number of profiles in a given subplot corresponds to the number of stars that preferred the given profile. Okay, so in this case, for example, there were 3 stars that preferred having a combined exponential diffusive overshoot and constant envelope mixing. So what you're seeing here is, first of all, there's no one single profile that fits all stars the best. And the levels of mixing appears to be quite diverse across the entire sample. What we do see, though, is that there are a higher number of stars in this bottom row, meaning that a higher number of stars prefer having this convective penetration prescription for the mixing in the convective boundary mixing region. And also there's quite a high number of stars that tend to prefer having this kind of stratified envelope mixing, which you can obtain when you have a rotational mixing inside the stars. Now, if we look at the parameters themselves, I'm just going to look at 2 different correlations that we found for the SPB stars. One of them is looking at the convective core size as a function of the amount of mixing we have in the envelope. So increasing number means the higher the amount of envelope mixing we have. These data points are color-coded according to the age of the star, measured as the ratio of the current to initial core hydrogen mass fraction. So the darker the color, the more evolved the stars are on the main sequence. And so what we're seeing here is, at least generally, when we move above a certain envelope mixing value, we see that the convective cores of the stars tend to be larger for increasing envelope mixing values. Another thing we found is a correlation between the level of envelope mixing and the critical rotation rate of the star, where we generally find an increase in envelope mixing with the rotation rate for the stars. So that's kind of what you expect to see from rotational mixing as well. One caveat to this is there's one outlier out here, where you see a slow rotation rate combined with a high amount of envelope mixing. So this is not the only example where this is the case. And to show that, I've included 2 additional stars that have been modeled, but were not included in our sample, where what is found is a slow rotation rate combined with a relative higher amount of envelope mixing as well. Now, with all these parameters, with all these estimates, what can be done is also try to predict what the helium core mass would be at the end of the main sequence evolution. So that's essentially what this next figure is showing, is the helium core mass as a function of the mass of the star. The black dashed line corresponds to the minimum helium core mass we obtained from our grid of models, corresponding to the minimum amount of mixing that's been included. And the points themselves have been color-coded according to the amount of mixing we have in the envelope. So that what I want you to take away from this plot is essentially that there tends to be a correlation that the higher amount of envelope mixing we have, the higher the helium core masses will end up being at the end of the main sequence evolution. So now I talked a lot about mixing inside the stars. The next thing I want to get to is rotation. So actually, in the case of rotation, we can actually study the evolution of the interior rotation of the stars without actually having to go into a detailed asteroseismic modeling. So you might remember what I mentioned earlier, that the slope of the period spacing patterns can be fit to estimate what the rotation is, and that can be done without having any additional asteroseismic modeling done. So for this step of the analysis, we increased the sample of SPB stars, including stars also studied using other telescopes, and independent estimates of the interior rotation rates for these stars. So in this case, we have a sample of 33 SPB stars, where we studied what happens to the interior rotation of the stars as they evolve along the main sequence. Each one of these subplots is essentially the same figure. The only difference is the choice of the age indicator that has been used. So in the left-hand panel, we have the core hydrogen mass fraction with respect to the initial hydrogen mass fraction. The central panel, we have the age of the star divided by the main sequence lifetime. And finally, on the right-hand panel, you have the surface gravity as a measure of the age of the star. So generally what is seen, independent of which age indicator is used, is that there is a decrease in the rotation rates of the stars as the stars become older. This result is slightly different or less clear, let's say, if you look at another group of gravity mode pulsators called the Gamma Dorado stars, which, like SPB stars, also have period spacing patterns that you can use to derive rotation rates. But these stars are F-type stars and much less massive, not quite as massive as the SPB stars. And so you see here from this sample of about 600 of such Gamma Dorado stars that no such clear trend is seen as for the SPB stars. Now, one immediate question you might want to ask is, well, is this just what we expect to see from stellar evolution? And so to investigate that, I had a look at 3 different scenarios for what's happened to the evolution of the rotation of the star as a function of main sequence age. using 3 different assumptions for the angular momentum transport. The first one being that no angular momentum transport is happening between neighboring cells in the models. The second one assumes we have solid body rotation and also are conserving the total angular momentum. And the final one assumes that we have angular momentum transport from the Stroit-Taylor dynamo. Now the plots here on the right corresponds to the colors, each one of these 3 different scenarios. The top rows versus bottom rows are the 2 different age indicators. Yeah, so we have hydrogen mass fraction versus actual age of the star measured in main sequence in ratios to the main sequence lifetime. On the left, we have the interior rotation experienced by the gravity modes, calculated as the average rotational frequency experienced by the gravity modes over their propagation cavity, weighted by the Brunt-Väisälä frequency. And on the right, we have what happens to the surface rotation. All of these profiles are scaled according to what the rotation is at the 0-age main sequence. And so what you can see here is that all 3 scenarios predict that the rotation for the star should be decreasing with age. But what we can look at is the kind of regions in the rotation versus age diagram that each one of those would predict for the 2 extreme scenarios. So for the next one, I'll just consider the case of solid body rotation and no angular momentum transport, and do a simplification and just doing a scaling to see what kind of regions those 2 scenarios would span in this rotation versus age diagrams. So in this case, the blue region corresponds to the cases of solid body rotation, where the orange hatch region is the case of no angular momentum transport. Each one of these black data points corresponds to the average and standard deviation of the stars with each one of these 4 age groups. And what I really want you to take away from this is that when we go to the older stars in the sample, the case of no angular momentum transport, there is an empty region up here where the case of no angular momentum transport predicts that we should be finding stars, which we don't. So essentially, we have a lack of old SV stars with higher rotation rates. And so all this is really telling us is that it seems angular momentum transport is indeed happening inside these stars in the main sequence, and it might also be quite efficient. Now, one additional thing we can learn from studying these rotation rates combined with a spectroscopic rotation measurements is to try to estimate what the inclination angles of these stars are. So this we can get from the rotation frequency of the stars combined with an estimate of the radius of the stars, which we, in the cases where the stars have been asteroseismic modeled, we have an asteroseismic radius. For a few of the stars, no asteroseismic modeling had been done before. So in that case, the radius had previously been obtained by comparing the positions of the stars in the HI diagram with evolutionary tracks and getting the radii from such models. So in the figure here on the left, I'm showing you what the V sin I values are compared to the derived equatorial velocities under the assumption that the stars are rigidly rotating. The size of the symbols corresponds to the highest amplitude signal that's included in the period spacing pattern. And so what is seen here is kind of a general trend that the slower rotating stars appear to have higher amplitudes. So that kind of could explain why ground-based studies of slowly pulsating B-type stars tend to have found mainly these stars to be slowly rotating, as those stars would have been much more easy to find from the ground compared to more rapidly rotating. So now that we have these estimates, we can go on and derive what the inclination angles are. So that's what I'm showing you here in the central plot right here. And I'm showing you what the inclinations are according to the azimuthal order of the oscillations themselves. So what you're seeing here with the distribution of inclination angles is that for retrograde and prograde oscillations, so cases where we actually have nodal lines that cross the equator, the inclination angles, we don't really find any of the stars having lower inclination angles. And that's kind of what we expect from a surface cancellation effect standpoint. So on the right here is a prediction of what we expect kind of to happen with the visibility of the oscillations as we change the inclination angle. So the darker the color, the higher the visibility of the oscillation would be. And for higher inclination angles, we expect these prograde and retrograde mode to be more visible than these m=0 modes. So why is this the case? Again, this has to do with surface cancellation effects happening for the stars, where again, for the cases where we're seeing the stars pole on, and none of the modes are crossing the equator, essentially all of these segments on the surface of the star, the changes in the flux that those cause end up canceling each other out. And that's why we don't we have a lower amount of modes that we can find for high inclination angles for these m=0 values. In contrast, if we move to the modes where all of the nodal lines cross the equator, those are more visible when we see them equator on, but the surface contribution kind of cancels out as we observe the stars pole on. So to summarize the results I've covered for this talk, I hope I convinced you that asteroseismology is really fun and cool and can tell us a lot about stars. Asteroseismology allows us to infer what the interior mixing profiles looks like for these stars. We carried out the first ensemble asteroseismic modeling of 26 Kepler SBB stars, finding that the mixing is very diverse, but the stars seem to prefer having a kind of a stratified envelope mixing happening. We also find that near core rotation frequency appears to be decreasing with main sequence age, and that the distribution of the rotation frequencies seems to be indicative that the stars do have efficient angular momentum transport happening on the main sequence. So now, aside from the science, I promised I would also cover a bit about the University of Sydney itself, where I'm at, and what kind of opportunities, should anyone be excited to come to Australia to do some research. Surprise, surprise, University of Sydney is located in Sydney, Australia. And if you want to come and study, there are various opportunities for doing that, or if you have students you want to send here, there are various opportunities. So on one hand, the way the education looks like, the structure of it, is we have undergraduate and an honors degree, which is similar to a combined bachelor and master's degree that you do. The start of the academic year is in February, so there's plenty of time still to try to apply to come to Sydney. As also undergraduate and honors students, if you know anyone who might be interested. Aside from that, if you want to come and do a postgraduate degree, know someone who might be interested. So that corresponds to a PhD degree. The important part here is really to try and find a supervisor before starting to apply. So the normal process this would work is you look for someone in the, for example, Institute of Astronomy, in any of the fields that are being studied, have a chat with them, see if they'd be interested in taking on a student. And if so, you send in an application for a PhD scholarship with a deadline in September and December. Now, if we want to look at the Sydney Institute of Astronomy, there's various different research fields being undertaken at the university, at the School of Physics. So it both covers stars and exoplanets. There's also instrumentation, galaxies, galactic archaeology, radio transients, solar physics, and astroparticle physics. So there are a lot of different fields. It doesn't have to be just, if you look at the stars group itself, of the asteroseismology group in Sydney. The group is currently expanding, and we have at least one new postdoc and PhD student starting in the next couple of months. And we also have weekly meetings, including the asteroseismology group from New South Wales, is University of New South Wales, and also University of Hawaii. So there's ample opportunity to collaborate, not just with people in Sydney, but also at different asteroseismology groups outside of Sydney. Something I want to highlight here is, on one hand, Yaguang is currently defending his thesis, so please send him in a lot of good energy. Aside from that, should you be interested or know of anyone interested in applying for postdoc positions or PhD positions in asteroseismology, its embedding will be putting up advertise new positions in the fall for such. It's not a requirement that you're an expert in asteroseismology from the get-go. We're more than happy to welcome people who want to learn and know a lot more about asteroseismology than they might do so already. Aside from this, I wanted to mention final opportunity. If you want to learn a lot more about asteroseismology and are curious to what's happening inside this field, and also maybe aside from slowly pulsating B-type stars, there is a conference happening in July of this year in Hawaii. Abstract deadline is still open for contributor talks, so feel free to submit a talk and come to Hawaii and learn a lot more about asteroseismology in general. And with that, I'll say thank you all for listening, and I'm happy to take questions.
Okay, thank you very much, Mai, for this really interesting talk. I'm sure that you have not only convinced us that asteroseismology is cool and fun, but also that is extremely useful. So now is time for questions. And in addition to the more senior people and experts on asteroseismology, I really encourage students and people from other topics to make questions to me, because it's a very good opportunity. So let's go for it. I think we have first Joachim Puls. So please go ahead.
Oh, thanks a lot for this very instructive talk and the nice results. I have one general question, which I'm always asking, and the answers are, in my opinion, not always very satisfactory anyhow.
Okay.
So to my understanding, many of your results depend on the correctness of the underlying evolutionary models, because when I understand this correctly, you are disturbing these underlying models. And so my question here is particularly regarding the angular momentum transport question. I mean, MESA has not very much choice about angular momentum because it's done in a diffusive way. So what would you think about the impact if you would do this more correctly, at least in my opinion, namely if you would use advective transport in the models? Right.
So it's what I've done is indeed quite simplified. So I agree with that also for the MESA models. I think something that's important to do when trying to study this is also, on one hand, increasing the sample itself. So right now there are, for example, not that many young SBB stars where we have a rotation frequency measurement. And we want to really also, it's in a sense still spanning quite a wide mass range. So something I would like to do is try to increase the sample. And then by doing that, I think we can get much better constraints, and also by using maybe more sophisticated ways of including angular momentum transport in these types of models. So I'm certain advection is definitely going to have an effect.
But you cannot change the general outcome from these models. That's a problem, I guess. Because when you compare, for instance, models with diffusive angular transport and advective one, you find, I don't know now for the early type B stars, I must admit, for the low mass B stars, sorry, I know only more about the O stars, but there are very big and large differences in the outcome, even in the early evolution. And so are there any plans to compare with models, with the really other models, not only these MESA ones?
Right. So I'll say on my end, I don't currently have plans. I think that's an exciting project to take on, and I think that would also make a fun potential PhD study to take it on, for sure. So I'll say I've been tempted to move on to working on OB associations observed by TESS. So currently the SPB stars from Kepler have been put a bit on hold. So it's certainly something that I would highly encourage someone to take up and have a look into what the stars would tell if you also use models from other codes, let's say. So I guess the difficulty is also making sure that when you're setting up the models, you're making sure that at least the basic input physics are similar. Yeah. And then you can change, again, the rotation and how that's implemented. Yeah, so it's not something I have on my plate. I think it's important to do. And if there's someone who would be willing to take that up, please feel welcome to do so, or have a chat. Happy to have a chat about this as well. Yes, at the moment, unfortunately, I don't have any plans to work on this directly.
Okay, thank you.
Okay, so we can go to the next question by Dominic.
Mm-hmm.
Hi, Mai, do you hear me?
Yeah, I do. Hi, Dom.
Hi, nice to see you talk about this in a very clear way, and excellent as always. I'm in a room full of Leuven people, so you can assume that there's 15 people watching here. So it's really interesting to me, this result about the old stars being slow rotators. So I was just thinking during the talk about the BE star phenomenon. So these are the rapidly rotating B-type stars, and they do pulsate. So I'm just curious whether this is a physical mechanism, or is this maybe an observational bias that with the tools that we currently have, we're more targeting the slowly rotating stars, but the BE stars also pulsate, and they are just effectively missing from the sample.
Yeah, so I think that could definitely also be the case. And I mean, also when you look at the younger stars, so the sample again here is biased because we don't have that many close to 0.8 main sequence SPB stars that we're studying. So some of these things might be explained also if you manage to increase the sample and can really include more of the younger stars. So yeah, again, it's possible also including more of the BE stars. So I believe there are 2 in the current sample here, and having more of those would, I think, also maybe shed some light onto different, again, angular momentum transport mechanisms happening for these stars. So I think that's definitely valuable to look into. It's not anything I have an answer to right now, unfortunately, but yeah.
Yeah, I think it's really interesting to look at the BE stars as like a distinct population, especially if they come from a post-interaction binary scenario. So do you have any sort of ideas of how we could filter them out from them effectively being single now, but maybe binary in the past? Does that show asteroseismically somehow?
Yeah, so that's actually, that's a topic I have on my research plate at the moment, actually. So one of the studies I'm trying to carry out also with Mathieu Renzo is to look into comparing the 2 scenarios if you have a post-accretion binary products and seeing what the gravity mode pulsations are predicted to be for those, and then try to model it as if it was a single star and see if you can actually distinguish between the 2 scenarios. No results yet on that, so that's a work in progress. And something I'm very excited to do. There are trickeries involved when you have highly rotating stars rotating near the critical and want to derive oscillation frequencies for such models. So there are some tricks you might need to implement when doing so.
Okay,
so
very
yeah,
exciting. Yeah. Thanks. I'll say goodbye from everyone in the room as well.
Hi.
Okay, thank you very much. I have a curiosity myself related to this question by Dominic. Is related to the available observations, because Kepler was great. TESS is also great, but the number of targets with large enough or long enough time span is limited. So what have you learned about the minimum time span that you need to have good measurements of these period spacings? and do this kind of studies?
Yeah. So I will say it depends a lot on where exactly in the sky the stars are located. So if you're in the continuous viewing zone, where you have the 1 year of continuous observations, then for those you can identify the period spacing patterns.
Mm-hmm.
As soon as you start decreasing and having just, let's say, 2 sectors, observe 1 year, and then a year later you have observations of 2 sectors again, that's a lot more complicated to do the analysis in those cases. Also because the gaps in the data is going to mess up your Fourier spectrum a bit and introduce alias frequencies. So you need to be really careful when you're extracting frequencies to make sure you do the right ones. And also they're going to influence the amplitudes and make things a lot more complicated. Exactly how big of gaps you can allow and how small, let's say, the length of the time series can be. So I believe you can go down, if you're just looking at half a year to 1 year of continuous observations without any additional gaps, I believe you should still be able to find the period spacing patterns.
Mm-hmm.
If you start breaking it up into smaller segments, but then observing multiple times in consecutive years, my hope it's still possible. So that's something I'm looking into now as well, and having some students here try to compare data from Kepler with data from TESS and see if they, from a subsample of these stars as showed here, can still find the period spacing patterns.
Yeah, because I think this is going to be very useful, because then in connection with all the spectroscopic surveys that are now ongoing, to really, because at the end we need the confirmation from a spectroscopy that this is a B star or a B, no? So it would be great. What are the regions we need to concentrate to really try to find the good targets for these kind of studies, no? Okay.
Yeah. And that's certainly predictions we can make.
Great. We had a question by someone that is not there anymore. So is anyone wanted to add a question? So Facundo again, yeah, it was Facundo. Go ahead, Facundo.
Can you hear me?
Yeah, a bit.
My camera doesn't work, I'm
yeah.
sorry. Well, never
Go
mind.
ahead.
So my question was about the G4 type stars, the one that are close to the end of the main sequence. And I was wondering about potential selection effects at high rotation rates, because, for example, for gamma Droz stars, we know that it's more difficult to obtain the rotation rate of the G-mode cavity if the star is rotating fast. So, are there any selection effects, or do SPV stars suffer from the same problem?
Well, in that case, I think it's more a matter of, with respect to the critical rotation rate, that's important. So that does change a bit. I don't think it's from measuring the slope of the pattern that's causing the issue. It's more, how many stars it has been looked at, I guess. So you want to increase the sample essentially.
Yes, but at the end of the main sequence, especially, because if you see that there is a lack of fast rotators, well, what will be the reason? Is it the selection effect really, or is it that the stars are really slowing down? Because that would really discern whether the transport of angular momentum should be efficient or not.
Yeah, well, so they are expected to slow down with stellar evolution, for sure. It's just the rate at which they are slowing down depends on what kind of angular momentum transport you are adopting for the stars. So the decrease in rotation is expected, but how fast it happens depends on what kind of angular momentum transport you're happening.
Yeah. Okay, thanks.
Okay, any other question came from the audience? If not, I have a lot of questions, but I will ask only one. It's just curiosity. So you were showing that, if I understood correctly, when you have pole-on stars, certain the amplitude of the pulsation are going to slow down or to go down. So can be this used as a way to separate real low vicinal star or low rotating star from a fast rotating star that is simple long, in terms of you measure the vicinal and also the amplitude of the oscillations. Because if it's a really slow rotators, you will see the large amplitude variability. But if it's a low vicinal star that actually is a fast rotator, your amplitude is going to be lower. Has this any sense? Or
yeah. So that's easier to do when you have slowly rotating stars. So for slowly rotating, so what's essentially happening when you introduce rotations is that you end up splitting up the pulsation frequencies, and the separation depends on how fast the stars are rotating. So in the case of a slowly pulsating star, the effect of rotation is kind of you can treat as a perturbation to the stellar oscillations. When they're fast rotating, or at least their rotation frequencies are similar to the pulsation frequencies of the stars, which is the case for most of the SBB stars, then you see a general frequency shift, and it becomes a lot more complicated to study. But so for the case of the slowly pulsating stars, when they're becoming rotationally split, I might even be able to show, because I had a few extra plots. It's demonstrated here essentially. So when you have slowly rotating stars, well, when you add in rotation, your frequency is going to be split up to, and the number of frequencies you have depends on the degree L of the oscillations. So the higher the L value, the higher the number of frequencies, peaks you get. And so by studying these, for example, in the case where you can see all three oscillations, let's say from the rotational splitting, the amplitudes change depending on the inclination angle. And so it's easier to see, for example, if you have a case where you're only seeing the -1 and 1 M modes and don't really see the M equals 0 modes, then you know that you're close to viewing the star pole on, contrary to cases where you have viewing your equator on, where it's easier to see the other modes.
Okay.
Yeah. It's more easy when you can see the actual frequency split modes. And for the SBB stars in my sample, there are only 2 of those where you can really see that frequency splitting. So that's really effective for most of these stars, even though we say fast rotating or slowly rotating, it's really only 2 of them that are really, really, really slowly rotating in the sample where you can easily see this kind of frequency splitting.
Okay.
So if you go up in mass, fortunately, to look at the P-mode pulsators, so beta Cephei, where you have the P-mode pulsations, that should be a bit easier to see, also because the frequencies of the oscillations are a lot higher. And so there's a much wider range, let's say, where you can have effects of rotations play in. So it's the oscillation frequencies are going to be a lot higher than the rotation frequency. So it's easier potentially to find these rotationally split nodes and then study that part.
Okay, this is very good news. That's going up in mass. There will be things, interesting things to do.
Yeah, still need to find kind of slowly pulsating. The slower rotating they are, the easier it is to find.
Okay. So then last chance to make questions to me. If not, as usual, you can contact her. The talk will be also stored in our YouTube channel, so there will be more chances to really ask questions. I don't see any hand here. So again, May, thank you very much for this really, really good talk. And I hope you enjoy very much your stay in Sydney. And you have convinced some people to go there and continue what you started. Okay, and we'll have our next seminar in 1 month, the last Thursday of May. and this time will be Michael Abdulmashid. So we hope that people will be here, and I want to also thank all the people coming to watch the seminar. Ciao, ciao.
Thank you.
Thank you, Mai.